Good morning and welcome to this next lecture on vibrations of plates and shells. So we are looking at the Rayleigh Ritz method for estimating natural frequencies using approximate functions, which we call admissible because they satisfy only the geometric constraints. And last class we did a cantilever beam example and I showed you this table which tells you the estimate of the natural frequency parameter as the number of terms are increased. Okay. Now this Rayleigh Ritz method is versatile and you can do many other things with it, or rather you can look at even complicated systems with it. So we will look at one complicated system. A more complex system. More complex system. So the system is this. So we have a cantilever beam still, okay, but and let us say that is L, that is full L, let us suppose it is L over here. Okay. And then at a fraction of that length, I have a disk which is A times L. Okay. A is a fraction. Okay. So this disk has a mass moment of inertia I0 about this axis and a mass m0, and then further at some point there is a spring attached locally at one point, and where is that point? That is also at a fraction of the length, which is B times L. So this is B times L. Okay. So can we find the relevant matrices for this system using Rayleigh Ritz? Okay. So now again the f of x, okay, I will use the admissible functions which are j equal to 1 to n, gj, phi j, bar, let us say. Okay. In it the same ones can be used, x over L whole square, x over L whole cube. These are admissible functions, they satisfy the conditions here and here. Okay. And so they can be written as phi, phi, how did that happen? Phi j bar, okay, and we will write them as x over L j plus 1. Okay. Now the potential energy in the beam Bm is whatever is there with the beam earlier plus that is brought in by the spring. Okay. So this now becomes integral 0 to L E I by 2 f double dash of x whole squared dx, okay, plus k by 2. So this spring constant is k, okay, k by 2, and the deflection squared at BL squared. Next, the kinetic energy function. Kinetic energy function. So what is that? That becomes psi max as psi, that is from the beam, plus psi now from the extra mass, plus psi. So this due to linear velocity and this due to rotational velocity of the mass. Okay. So as this beam vibrates, this mass translates up and down, it also rotates back and forth. Okay. So you have to include both the kinetic energies. So these are the two terms. Okay. So how do you bring them in? That is equal to integral 0 to L m by 2 f of x squared dx, plus this is the linear velocity term from the mass, m0 by 2, okay, f a l whole squared. Okay, because the omega is separated out, omega square is separated out, plus I0 by 2, and here comes the rotation. Okay, okay, W was the displacement, W dash is what we take as the rotation at a section in Euler-Bernoulli beam theory, if you recall. Okay, beta is minus del W by del X. Okay, so I0, now the derivative at AL and squared. Okay, so this is beta squared. Okay, so now what is Kij? We have seen last time the elements can be very nicely obtained. Kij, the ijth element in the K matrix, this is equal to del 2 by del Gi del Gj integral 0 to L E I by 2 f double dash of x squared dx plus k by 2 f of BL squared. Then we have del 2 by del Gi del Gj EI by 2, okay, integral 0 to L. Now summation of j from 1 to n, the weight, the double derivative of the admissible function squared dx plus k by 2, the displacement j1 to n, coefficient phi j bar at the location all squared, all things squared, and bracket closed, and a d no sorry yeah, this is at a specific point. Okay, please note that there is no integration related to that, please note. Okay, this is at a particular point, whereas this is over the x. It's important. Okay, then what do we get? If you perform this properly, I am shortening it, you get EI integral 0 to L phi bar double dash I phi j double dash dx plus k phi I bl phi bar j bl. Okay, so if you now find out the element kij I comma j, it will look like I plus 1 into I j plus 1 into j E I by I plus j minus 1 L cube, and the spring part k b I plus j plus 2. These are the elements of the stiffness matrix. Okay. Now similarly, the mij part works out to be del 2 del gi del gj, okay, of the integral 0 to L m by 2 f of x whole squared dx, this is for the beam, plus m0 by 2, this is for the linear velocity of the mass squared, plus I0 by 2, the slope or rotation at that location squared. Okay, and just at what is, because it was at a point, no integration. Okay, so if you do this derivative, you will get m integral 0 to L phi I phi j dx plus m0 phi I at AL phi j at AL plus I0 phi I dash AL phi bar dash j at AL. Okay, so now if we put it after this integral, how does it look? The ijth element in the mass matrix looks like m L by I plus j plus 3 plus m0 a to the power I plus j plus 2 plus I0 I plus 1 j plus 1 a to the power I plus j. Okay. Then you form the generalized eigenvalue problem k into g minus omega square m into g and set it to 0. When you solve this, you will get estimates for the natural frequency. Okay. Then you compute the eigenvectors. You get, let us say, omega 1, omega 2, etc. Then you substitute it back here for omega and you find the corresponding eigenvectors. G, so G1, G2, etc. Once you do that, if you go back to your f of x, which is a summation, let us say, over g, gj phi j bar, if you do that, then that will give you the mode shape, the mth mode shape. Let us pull it GJM here for the mode shape corresponding to the mth natural frequency. Okay. So I have shown you a slightly more complicated system. Now this course here is not so much related to choice of proper admissible functions. Because this is more basic theory, okay, about proper admissible functions that are good for numerics, good for numerics, and that give good matrices, what shall I say, matrices good condition numbers and so on for inversions and numerical analysis. Our focus is not so much on that. Okay, our focus is to present basically the number of methods you have. So we have seen how you can put additional local elements in a Rayleigh Ritz setup. Okay, yet it would be nice to know a few other methods that are there. Okay, and the reason being that these sort of functions that we use, x by L whole squared, x by L whole cube, x by L fourth, these are what we call the simple polynomial. Okay, they are very simple in the sense that you can integrate them and manipulate them easily in a numerical setup, but they do not provide nice matrices. Okay, good matrices for numerical calculations. and therefore I am just making a general set of comments. Okay, as I said, our focus is not on numerical analysis. So this sort of set of functions, they do not provide, if you go higher in numbers, let's say 5 terms, 6 terms, the matrices that you get, they are not very good for numerical manipulations, inversions and so forth. Okay, and so in this Rayleigh Ritz method, choice of admissible functions is a big game, game in the sense of challenge, the big challenge. Okay, and so that these functions will satisfy a set of boundary conditions here one end, and set of boundary conditions there at the other end, and so forth. Okay, so now an alternative here is that you find functions. So this is one other method. You find functions that are not admissible all the way for all conditions, are not, so strictly not admissible first. They are strictly not admissible. What do they mean? That is, they satisfy some boundary conditions. They satisfy some boundary conditions, some of the boundary conditions, some of the boundary conditions. Okay. So now, how do you satisfy the other boundary conditions? Okay. So that means you probably found a reasonable set of functions that numerically are very nice to manipulate, okay, use in matrix calculations, inversions, so forth. Okay. Yet at this point they satisfy only some of the boundary conditions. So what do you do with the other boundary conditions? There you suppose there are constraints, okay, then there you use the Lagrange multiplier. Lagrange multiplier. So you have found a set of functions that are good for numerical manipulations, but not totally admissible. Okay, so there is some advantage, some disadvantage, and there are some constraints that they do not satisfy now. So how do you satisfy that constraint? You use a Lagrange multiplier. Okay, some of you may know this method of Lagrange multipliers. Okay, they force the functions to satisfy certain conditions at certain points. Okay, otherwise they give a penalty. Okay, so let's say now, so this is an example. So we are now taking an example. Okay, so this is now another method. Taking an example of a cantilever beam, okay, but now restrained at the free end. Okay, so now what is it? We have a cantilever beam. Okay, we have a cantilever beam, and normally what is it? It is free at the other end, so that it vibrates in these modes. That is the first mode, or that is the second mode, okay, etc. So it is free at this end. This is x equal to 0, this is x equal to L, that is the normal cantilever beam. But now what do we say? We say is that we want to put a constraint. That means the beam could be vibrating like this, but here it has to be pinned. So you have to have 0 displacement, it is 0 slope, that is for sure, okay. But here it is restrained by a pin, okay. So now for one thing you could find proper admissible functions that satisfy all the conditions, the left side and right side. Let's proceed. However, as I was saying, that let us say you have a set of admissible functions, hypothetically, okay, functions that satisfy the left side conditions only. The displacement and slope are 0, suppose, and otherwise they are good, okay. Otherwise for numerics they are very good functions. They give matrices with good condition numbers and so on, okay. And let us say you want to stick with them, okay, you want to stick with them, then what do? You take the same. So hypothetically we are going to do it, okay. So we are going to take the displacement W of x comma t to be this mode shape times the natural frequency of vibration, and so I am going to take the same admissible functions good for the cantilever case Gj, good for the cantilever case Gj x by L j plus 1, okay, j going from 1 to etc. Okay. So we will do a case with n equal to 2, so that you will see what I am pointing out. So here if I take n equal to 2, then my functions are x by L squared and x by L cubed, okay. Now you can see that f at 0 is 0, okay, with both of them, and f dash at 0 is 0 with both of them. However, f at L, okay, is not 0, is G1 plus G2, G1 plus G2, okay, because this is 1 at x equal to L, this is 1 at x equal to L. So my f at L is G1 plus G2, which is not equal to 0 typically, okay. So how do you now enforce this condition using these not fully admissible functions? So that is the Lagrange multiplier method. Okay, we are just about out of time, so we will continue this in the next class. Okay, thank you very much.